Hi everyone, my name is Will DeBerger, and I'm president of AIAA UW-Madison and the lead for Badger Ballistics rocketry team. We are excited to be competing in Argonia Cup for our first time this year, and we're ready to show everybody what Badger engineers can do. For this competition, we are required to launch a golf ball payload on a rocket to an apogee of greater than 8,000 feet. Then, the payload must be recovered at a predetermined location, in our case by a deployed glider. The flight profile for our golf ball payload consists of 3 distinct phases. Ascent, where our rocket brings the payload past 8,000 feet. Ejection, where our payload is deployed from the rocket at apogee. And unpowered glide, where our drone will navigate to the landing site. Beginning with the ascent phase, we will use our rocket to launch the payload to over 8,000 feet before deployment. Our rocket is 91 inches long and has a diameter of 4 inches. The 4 fins on the back will provide a minimum stability caliber of 2. Using an L851 motor, the rocket will reach an apogee of 9,200 feet above ground level, where the glider and the drogue chute will be deployed. At 500 feet, our 78-inch main parachute will deploy, which will bring our rocket to a gentle landing. The structure of the rocket is made of fiberglass and is composed of 3 main components. The aft body tube, which will contain our motor tube and the main parachute. The forward body tube, which contains both the coupler integrated avionics bay and the payload bay, where our glider and drogue chute will be stored. And finally, the last component is the nose cone, which is integral to our glider and will separate from the rest of the rocket at apogee.
Hello, my name is Isaac Becker. I worked on electronics alongside Kyle. We chose to use Arduino to control the sensors due to its ease of use and adaptability. The Arduino will control the temperature and pressure sensor, the accelerometer, the radio, and GPS as well. These are backup sensors and will send the data via radio to the ground. Our primary altimeter will be a MissileWorks RRC3. At apogee, it will have the ejector charges activate and have the drone detach, as well as deploy the drogue parachute. We will also have a backup tracker and altimeter to ensure that our rocket is able to be found and the ejection charges activate at the correct time.
Hello, my name is Finn Roberts and I am the drone lead. Our payload landing vehicle is a glider-style drone. It has main wing and a 45-degree dihedral tail. The main wing includes ailerons and the tail wings themselves are the control flaps. While in the rocket, the main wings fold backwards and the tail wings fold forwards. The nose of the rocket redoubles as the nose of the drone. The drone itself has a wingspan of 36.5 inches and is 37 inches long, including the nose. It has a carbon fiber frame and a parachute will be stowed in the location below that will deploy for the final stage of landing. All electronics are stowed inside the nose cone and fuselage, forward of the wings.
Hello, my name is Sam Yeager, and I'm the aero lead. So first, to determine the aerodynamics of the drone, we modeled the aircraft in XFLR5. This program uses Xfoil to gather 2D aerodynamic data, and we used a NACA 4412 for the main wing and a 0012 for the VTAL. From this 2D aerodynamic data, we used a nonlinear lifting line code to determine the aerodynamic properties of the wing-tail combination for a range of speeds and angles of attack. Combining this 3D aerodynamic data with the mass properties determined from our CAD model, we ensured the stability of the aircraft. When our aircraft is fully assembled, we will verify the stability and aerodynamic performance of the drone to further refine our model.
Hi, I'm Kyle, the electronics lead for our team, and I'll be going over the electronics in our drone. To control the drone, we're using a commercial off-the-shelf flight controller, the Motec F405 Wing. We chose this flight controller for its versatility in hardware compatibility and software support, and it will be running ArduPilot's ArduPlane for GPS waypoint capabilities. ArduPilot was chosen for its widespread use and easy mission planning. The ailerons and tail wings will be controlled via servos, the latter being actuated by the larger of the 2 types of servos.